So let me first introduce Rafay. Rafay is a senior principal scientist at Amazon Prime Video and Amazon Studios, where he is the co-founder and the chief scientist of multiple game-changing AI-driven experience across them, such as virtual product placement, global compliance and moderation, immersive sports customer experience, personalized marketing access generation, and video quality evaluation, which are featured by BBC, Time, MIT Technology Review. And he also contributes a bunch of great top-tier research papers that inspire the community very much. So let's warm welcome Rafay and hand it over to him. And you will have 25 minutes for the presentation and 5 minutes for the Q&A. And friendly notice is like, please disable the annotations for others to avoid unexpected bump.
Sounds good. Just wanted to confirm, can you hear me well?
Sure.
And can you see my screen correctly?
Yeah.
Okay, cool. Thank you. Thanks so much for the invitation and for the kind introduction. So my name is Rafi Hamid. I'm a scientist in Prime Video and Amazon Studio, and I'd like to go over some of the work that we are doing in the space of computer vision and machine learning for long form video understanding and synthesis. So Prime Video obviously serves a lot of different types of video content for our customers, including Amazon Originals. We have a whole bunch of different channels that we offer to our customers as well. Customers can watch ad-supported video on our freebie service, as well as that creators can actually upload content to Prime Video Direct in a self-service manner. And last but not least, we have a growing footprint in the space of live events, especially with the investment in NFL, etc. That's a growing area for us as well. And so given our very wide selection of content as well as global customer base, it is really important for us to invest in AI technologies in order to be able to continually delight our customers in a scalable and efficient manner. Right? So in today's chat, I'll be giving you guys a very high-level overview of some of the stuff that we're doing in long-form video content, particularly in the space of content understanding, as well as content synthesis. And to give you folks a little bit of examples of some of the stuff in content understanding specifically, we're using AI technologies for automatic marketing asset generation at scale, like promos and cover art generation. We're also doing actor tagging at scale in order to provide a lot of information about what are the actors that are appearing in the titles that our customers are watching. We are using AI to ensure that the highest quality video is actually delivered to our customers. Similarly, it's not just the visual information in long form videos, but also audio is extremely important to us. So we're performing a lot of different types of audio analyses as they are powering a whole bunch of different downstream use cases for us. To ensure the customer safety and trust, we are performing large scale content moderation and compliance in long form video. And just to present one last example here, we are starting to use AI technologies for optimal video encoding as well. So this is just to give you folks a little bit of flavor of some of the stuff that we're doing in content understanding. Similarly, in the space of content synthesis, we have a big new initiative of virtual product placement. And so how do we insert products into long form videos in a photorealistic way? And that requires us to really rethink how traditional VFX processes are performed in the industry. And I'll speak a little bit about that in a second. Similarly, in the space of live sports, we are trying to use AI to understand what is going on and then synthesize and generate different types of sports visualizations to make our customers more engaged with the content that they're watching. And last but not least, we are using AI to synthesize human speech, human voice in order to create audio descriptions at scale to improve the accessibility of our video content. So this is just a very high level, broad brushstroke of some of the stuff that we are doing in this space. Let me start by double clicking a little bit on the content understanding bits for the next few minutes. So while there are a whole bunch of different technological challenges in the space of content understanding, like modeling and evaluation and large scale deployment, I believe that one key problem that cuts across a lot of different use cases in this space is label acquisition. And there are three key reasons for this. And the first one is that majority of the AI models that we are still using in the industry are still, they require strong supervision through labels. And then, collecting and managing and cleaning these labels is a significant portion of what our scientists do and they spend their time on. And it's a little bit of a decelerant for us. And then I would argue that the long form nature of our content makes the problem of label acquisition and label management even harder than some of the other spaces like text or images. And so as we try to address this problem at scale, we have to keep Prime Video's unique setting in mind. And there are two important parts of that. And the first one is that our video catalog size is very large, right? So we have a lot of long form videos available to us. And then the second key factor is that we have petaflops of compute available to us to use that, right? And so while keeping both these unique aspects in mind, the big question that then becomes for us is, how do we learn effective content representations while requiring minimal number of label data and at the same time making maximal use of the raw videos that are available to us? And so there are the whole bunch of different ways to approach this question. And one of the most promising directions that is coming up in this space is contrastive learning. And so in today's talk, I'm going to spend a little bit of time talking about some of the example applications that we have explored in the space of content, contrastive learning for applied for content understanding. And so these three examples are scene boundary detection, which is a very task-specific problem. And then the second area is learning more general purpose representations that can be then applied to achieve state-of-the-art results for a whole variety of downstream tasks. And then the last example that I want to talk a little bit about is cross-modal pre-training for applications like auto-tagging or search and retrievals, etc. So let's chat a bit about scene boundary detection. So before going into any further details, let me concretize a little bit about what I mean by shots and scenes. And so here I'm showing you a few keyframes for one movie, Stuart Little. And when I say shot, using this illustrative example, what I mean is a series of frames captured over an uninterrupted span of time. And so here I'm showing you 9 illustrative examples of shots from this movie. And on the other hand, scenes imply a series of shots from a single location capturing a cohesive part of the story. So here I'm showing you 2 example scenes for illustrative purposes. And so just at a very high level, providing you an approach overview. So we start with a current shot in a series of shots that is given to us. And then we look at the temporal neighborhood of our current shot. And based on the other shots in this temporal neighborhood, we select the most similar shot to our current shot. And then we use the current shot as the query shot and the most similar shot in the neighborhood as a positive key. And at the same time, we randomly select multiple shots to be used as negative keys. And then this query shot, positive and negative key shots are then used in a contrastive learning setting in order to learn our shot encoder, which is then fine-tuned as needed to perform a 2-class classification for whenever a scene boundary is happening in a pair of adjacent shots or not. Just want to say a few words about the intuition for positive key selection and why do we think it works. So in contrastive learning, I believe one of the most important things is how are we augmenting our data and then providing it to the contrastive learning algorithm, right? Unless we perform that augmentation correctly, the contrastive learning will not be able to learn the representation that will be effective. And so to illustrate this point, let's take a look at this query shot. If we were to augment this shot using some of the more traditional augmentation schemes that have been used in contrastive learning, like flipping or change of color space, This type of augmentation does not incorporate any contextual information that these shots can have in a scene, right? We could start using the temporal aspect and just pick the previous shot from a current shot or the next shot from a current shot. But as you can see that the appearance of these previous or next shots can be completely unrelated to the current shot, right? And so they really do not provide us any useful information. On the other hand, by making use of the most similar shot within a temporal neighborhood of a current shot, we are able to make use of the underlying structure of the storyline that is already there and is carefully curated by the director or the editorial process. And that allows us to capture the context and appearance of the scene in a meaningful way, which then results into this approach performing effectively in practice. So just a high-level overview of the underlying insight here. I also wanted to share a few results about the types of scene boundaries that this algorithm can detect. So here, for example, is a typical type of a scene change example where the type of scene actually changes, the type of place actually changes, right? So before the scene boundary was detected, you saw the soldiers were throwing some grenades in a swimming pool, whereas after the scene boundary was detected, now you're in a completely different setting. Similarly, another common example of scene boundary is like the same actor can be in different contexts. So here, before the scene boundary, one actor is talking to a particular actor, whereas in the second scene, the same actor is talking to a completely different actor and is in a completely different setting. So here again is a pretty common example of the types of scene changes that happen in long form videos. And lastly, there are different types of genres where the narrative is quite continuous. So for example, in documentary settings especially, the narrative can be quite continuous. And as you can see in this example, before the scene boundary, even though the entire content is within a hospital setting, before the scene boundary, the couple is talking to each other and is looking a little bit worried, whereas after the scene boundary, we see a nurse walking down the hallway, which is clearly a quite different scene. So just very high level overview of some of the context where this type of algorithm works successfully. And so you're welcome to find more details for this work in our CVPR 2021 paper, where you'll find a lot more qualitative and quantitative results for this approach. Moving on to the general purpose representation learning for a wide variety of downstream tasks. Just the main motivation of this type of work is, again, we've seen works like clip and align perform actually quite well for a whole variety of downstream tasks in a zero shot setting. And so our goal is, how do we actually be able to do that for long form videos? And the key challenge, just like I mentioned in scene boundary detection, again, what is the right type of data augmentation scheme that we can apply that works for the long form videos, right? And the intuition that this work comes in with is that we want to use available movie level information like genre or synopsis or co-watch as means for data augmentation to learn a generalizable scene level representation. And what I mean by that a little bit, to provide you an approach overview for this method, we start with like a sort of movie level similarity. And like, for example, you can use co-watch information or you can use genre information to select pairs of movies that are thematically similar to each other, that are overall sort of similar to each other. And then with this type of information, we automatically select pairs of similar scenes in order to then learn a scene encoder through contrastive learning. And then this representation, this scene level representation, is then fine-tuned to then perform different types of downstream tasks, for example, place tagging, year prediction, et cetera, et cetera. And the key point I want to mention here is that the movie level information is at a very coarse level, which is like around 120 minutes, whereas the scene level representation that we are learning is at a much more temporally fine-grained level, which is around 2 minutes, which is quite interesting. So we have actually I wanted to share some example similar scene pairs that this method is able to find. And as you will see, so here I'm showing you two different movies. On the left is Need for Speed, and on the right is Fast and Furious. And these are considered similar based on the title level or the movie level similarity metric that we're using. And as you can see that like these two scenes that the algorithm finds very similar based on its learning, they are from an appearance-based perspective, they're actually very different from each other. But from a thematic perspective, they are actually very, very relevant to each other. They're both showing, scenes of a car chase, right? And so just to show you another example of the similar phenomenon, here I'm showing you again, left Need for Speed, right, Fast and Furious, two pairs, a pair of scenes which is considered very similar to each other, and both of them have two actors speaking to each other within a car, right? And then lastly, from again same pair of movies, on the left we are showing a scene where a bunch of people are talking, just like on the right, in sort of a calm setting, right? And so this shows that by using this title level information, you're able to effectively learn scene representation that actually does give you meaningful and relevant results. We've actually tried this approach on 14 downstream tasks, and it does provide us with state-of-the-art results on all of those 14 downstream tasks. So it seems to be quite effective. And then lastly, wanted to say a few more words about sort of cross-modal pre-training for things like auto tagging and search and retrieval. So, previous approaches in sort of cross-modal representation learning, like CLIP, they basically, try to minimize the distance between images and their corresponding text pairs while maximizing the distance of all other pairwise relationships that you may have. And while they have been extremely successful, they still suffer from two important challenges. And one of them is data inefficiency, and the other is the compute inefficiency, right? And so there are two key reasons for these challenges. And the first one is that as you build your data by sort of crawling the web, there can be a lot of noisy and inaccurate captions that you may capture. So here, for example, I'm showing you one caption, which is actually a file name, right, which is clearly incorrect. And then the second main reason for this challenge is like there are many correspondences that are not being modeled as efficiently and as effectively as they could be, which basically results in not modeling the semantic similarity between negatives correctly, right? And so we address these two key challenges by instead predicting soft alignments to capture the similarity between the negatives in a more effective way. And so basically our work uses self-distillation, knowledge distillation. And as you may recall that in traditional knowledge distillation methods, we have teacher model that makes some predictions that are then used by the student models. And one of the costs that we pay in traditional knowledge distillation methods is that we have two different models, one for teacher and one for student, right? And that can result in both memory as well as computational cost. And in order to avoid that, we propose a self-distillation method in a cross-modal setting where the same model is used as a teacher as well as the student. And so basically the self-distillation part of our loss progressively increases as we go through the process of training. And effectively that means that our student effectively becomes its own teacher. And just to give one sort of canonical example of what type of an actual difference does it result in, here I'm showing you one query of a cat lying on top of a chair in the living room. And so if you look at the top results retrieved by the CLIP method, you would see that while these results capture the chair and the living room part of the query very accurately, the cat part of the query is completely missed, right? Whereas if you look at the results from our method, you would be able to see that all the three key parts of the query are actually represented very effectively, which is just to give you sort of a high level understanding of like what types of result differences would you see from a qualitative perspective. And again, you can see, you can find a lot of quantitative and more qualitative results in our CVPR 2022 paper on this topic. So that sort of concludes my very high level overview of some of the stuff that we are doing in the space of content understanding. Moving on to content synthesis, I would say that, a lot of the work that we are doing requires, using some type of visual special effects. But the problem with visual special effects is that a lot of the workflows are extremely manual. And so they really cannot be scaled to the level that we want them to be scaled, right? And so there is a whole bunch of different types of processes that go on in traditional VFX pipeline, like match move, geo, rotoscoping, etc. I want to focus specifically on match move, which essentially is about tracking the camera that was used to sort of capture a scene. And so in order to automate this process, folks, one way to do that is to use traditional structure for motion approaches that can perform, that can track the camera and at the same time extract the 3D structure of the scene. The challenge is, however, that unlike previous sort of domains where SFM has been used, where you have a lot of parallax present, in studio produced content, you actually don't, you have very small amount of parallax. And that's because that's intentional, actually, because we want to not shake up the camera too much, and we don't, so that we can have a negative experience to our viewer, right? And so in order to overcome that problem, because traditional SFM methods don't end up working for studio produced content as well. So in this work, we have proposed to use sort of monocular dense depth estimators as a prior, in order to then be able to use more traditional SFM methods in a more effective way. And here you're seeing some sort of example shots that I'm showing, where on top we have the input, and bottom left we have the estimated depth of the depth of the point cloud, and on the right we're showing the sort of the camera motion and point cloud sort of in a joint way. And then you can start using these types of technologies to then perform completely automated hands-free match move for different types of cinematic content. And here you can see that you have shots where you have very limited kind of motion, all the way to shots where you have very sort of purely zoom in motion. And for all these different types of shots, and this approach is working quite effectively. And then you can, with this information, you can start inserting more complex models in the scene. So here I'm showing you one kind of bottle. Here I'm showing you two, and then you can start having multiple sort of objects inserted in the scene that kind of start looking more photorealistic and without any jitter, etc. In the results. And so again, in the interest of time, I won't be able to go into any details here, but you're very welcome to find more details about this work in our CVPR 2022 paper on this work. And just like for sort of studio produced content, we're finding the correspondence between the scene and the camera is really important. So is the case for the space of sports, right? And here I would argue that the problem is a little bit more limited, because generally the broadcast camera is actually standing on some sort of a tripod, and it generally demonstrates pan, tilt, and zoom degrees of freedom. And so again, registering how the sports field is appearing as the camera pans, tilts, or zooms as the game process progresses is extremely important. And so we've done some work where we are using both sparse features prediction as well as dense feature prediction in order to then combine them to be able to register sports field quite accurately. And then here I'm showing you an example result of this type of an approach, where once the field registration is done, we're actually back projecting the model of the field of the American football field back to the appearance of the field as it appears in the broadcast camera. And as you can see that the lines of the model are aligning almost perfectly with the corresponding lines on the field itself, which shows that the method is working quite accurately. And on the right side, I'm showing you the field of view, which was captured by the broadcast camera at a particular instant in time. And this type of a method does not only work for sort of American football, but we've actually tried it for US Tier 1, top 5 US Tier 1 sports like soccer, ice hockey, basketball, tennis, and it works quite effectively in real time. And once you have this type of information available to you, like, once you're able to register the field to the camera, then you can start thinking about a lot of kind of useful sports visualization experiences for our customers, right? So here, for example, I'm showing you a video where the notion of yards to go, which is an important quantity in American football, in a particular play is displayed in real time. And as you can see that, at 30, the yards to go is around 70. And as the player moves towards the left, at 40, it's about 60, at 50, it's about 50, and so on and so forth. It's actually performing quite accurately. And along similar lines, you can start imagining other types of use cases, like, for any play in soccer, what was the total distance traveled by the player who was actually leading an attack, for example, on the opposing team, and at the same time, sort of what was their instantaneous speed. So here you can see that, like, the instantaneous speed of this particular player went all the way to 11 meters per second, which is quite astounding. And offering our customers these type of insights makes them better aware of exactly what's going on. And then you don't have to limit yourself to sort of use cases that revolve around a single player, right? You can actually start extending them to use cases that have multiple players. Like, for example, in soccer, a very, very important foul is offside foul. And here we are showing a virtual offside line where at the time that the player actually passes the ball to the second to last defense player, they are actually beyond the virtual offside line, which essentially helps the viewer understand exactly what's going on. And this type of a particular use case is even more informative for audiences of countries that are not as sort of experienced in understanding the nuances of soccer, etc. And so again, you can find a lot more details about this work in our WACFI 2021 paper. So this was a very high level, broad brushstroke overview of some of the works that we are doing, both in the space of kind of content understanding as well as content synthesis. And I hope this gives you some understanding of the exciting directions that we are pursuing, and lots more to come. So yeah, happy to take questions at this point.
Yeah, thanks, Rafe, for giving such a comprehensive and great keynote. And I see the attendees, the participants are quite excited about the speech, and they raised up a lot of questions. The first question I think is about, like, they really admire the resources that Amazon Prime could have, and they wanted to know, like, whether they could also access such kind of data at such a large scale.
Yeah, that's a great question. So, obviously, as active member of the research community, we want to sort of contribute to that space. And we have started to do that, Ani, as some of you may already know, that for our depth-guided structure for motion work, we have actually publicly released the data on GitHub. And if you guys haven't checked it out, please check it out. So yeah, there is a lot of internal conversations that are going on in order to do that. How do we do that in the best way? Because obviously there are copyright related challenges that we have to face, right? And so we want to do it in the right way. We want to do it kind of in a way that is helpful and acceptable to all parties that are concerned. I just want to assure everyone that we are working hard on that, and hopefully we'll be able to kind of cover more ground in the next few months.
Yeah, that's very nice. And then another question comes out from the application side. He is interested about the potential application of thin segments and short segments.
Yep. That's a very, very important question. Yeah. So there are a whole plethora of applications for scene segments and short segments. Let me focus a little bit more on the scene segments. So the work that we did was primarily for ad cue point detection, right? So when you're trying to insert traditional video ads in long form videos, we want to minimize how disruptive they may be to our customers. So we want to maximize the experience quality for our customers. In other words, we don't want to insert ads at places that are within a scene, or at places where two people are talking and are in the middle of a conversation, and now you're showing us a video ad, right? That's not the experience that we are aiming for, right? So in order to figure out what are the optimal places where we want to insert these types of traditional video ads for freebie, for our freebie service, right? So that's actually where the whole work started. But you can imagine there are many other downstream applications, especially like video summarization and sort of marketing asset generation, etc. So there's at least half a dozen more applications that can make use of the scene boundary detection information.
Yeah, and I also personally subscribed to the Amazon Prime Video, and I love those functions like the tagging, yeah. And then another question comes from like is interested about like in the recent times we start to talking about long form videos. So what's in your opinion? So what are the tasks and applications that truly need long form video reasoning?
That's a very, very good question, actually. So yeah, even so the long form video space is unique in my opinion in two ways, right? The first is that a lot of the long form video content that we have are studio produced almost by definition. And so that means that there is an underlying story narrative, right? There's a story arc there, right? And so previous, as you guys know very well, a lot of the previous work in video understanding has focused on sort of, non-studio produced content. So that's one part of novelty. And that means that a lot, even if you're doing learning at a shorter temporal scale, like frame based or short based or scene based or clip based, etc., there are certain challenges that are still novel and very exciting. But going back to the specific question, I think if you start thinking about problems like video summarization, right? The long form aspect brings a whole new flavor on the table, right? We have to be very, very aware of very long duration dependencies. We have to be very aware of what does it mean to be a spoiler and how do we avoid those types of things, right? And I would argue even beyond that, right? I would say that for TV series, right? It's actually far more than 2 hours or 3 hours or whatever, right? You could have like, I don't know, 24 episodes, each around 30 minutes long, right? So in some sense, the long form nature of it can exceed to like maybe 12 hours or so, right? So that completely changes the conversation when it comes to how do we capture and model long form dependencies. And these days, like transformers are all the rage. And, as you know, there's a lot of ongoing works going on, and that's a completely unsolved. A lot more progress needs to be made in that direction. So that are some of the ways in which the long form aspect brings its unique flavor to the table.
And in this sense, and it also means like the multimodality understanding it also very critical, right?
Thanks for reminding me, Annie. Absolutely. Could not agree more. Yeah. So, and just to be clear, like multimodality here, the heterogeneity of multimodality is actually higher than how we have seen it in the past. So audio and visual modalities are obviously very important. And then, a small leap forward is text, so to speak, from a conceptual perspective. But I would argue that there is a lot of sort of discrete information that is provided by the providers like genre, subgenre, overall mood, etc. Those should be considered within the space of multimodality. And lastly, on IMDb TV, right? Like you have reviews, you have synopsis. So there's a whole set of multimodality that we have to incorporate in a kind of a more of a consolidated way. I don't think that has been looked at in the past, just because long form cinematic content was not as much explored in the past. Yeah.
Maybe one comment here, like I was thinking, like, so I guess like for language, for instance, we have a clear definitions of the atoms, right? Of the like at least the written language, right? So we know each word has a meaning. But in video, and especially in long form video, I don't think we have get to the point where we know what is the atom, what is the minimal unit we should use for like analyzing and understanding long form video, right? We may use the shot, but even within a single shot, there may be a lot of things. There may be sub tokens within that shot, right? So is there something you think like we should look at, or like we should do research in that space, trying to come out with those tokens, or simply uniform sampling across these long form videos and try to come out with the tokens from the model would work?
Yeah, it's a great point. A very, very keen observation. I think, yes, as you know, very well know, like right now, the sort of the default atom that we are using, atom of information, or just a unit of content that we are using in a lot of these types of works, both at Prime Video and in general, is short, right? But as you correctly pointed out, there can be a lot of nuances within a shot, right? And I think that here there is a huge opportunity for us to learn in a data-driven way, right? We don't want to overcommit to shots, but we also definitely don't want to commit to frames, because without learning how does the importance of one frame vary from another. I think it's an open question. I'm not aware of, please help me get better educated if you guys are aware of some of these works, but I think I'm starting to see some initial work in that direction. But the long form aspect of that is still sort of not as at the scale that we want it to be for actual cinematic content, right? Yeah.
Yeah. Great. Thanks.
Yeah. I think one interesting perspective is like you mentioned, like we have shot, we have scene, right? But like in history, people talk about like story understanding, right? So in terms of like long form content, do you have any perspective on, for example, what kind of story, right, we should be focusing on, right, to understand, really understand the movie content, right? For example, some people, they say, if I can generate the movie, right, for example, generate the plot, generate the story of the movie, so that means I really understand the long content, right, in a multimodality way, right? The kind of like you said, this is an open question, but I want to see if you have some perspective on those kind of.
That's a great question, Dong. I think that there are 1.5 points I'd like to make. So I guess one point is that the first problem that comes to my mind, which could be very relevant to the direction that you're alluding towards, is summarization. Right? So I would argue that a great summary of a long form title or a long form movie, or a movie, let's say, would be able to capture this underlying narrative or storyline that you're alluding towards, right? And so a promising direction could be, can we make use of some, there's a whole bunch of different efforts that are going on in the summarization space. Can we kind of make use of a lot of that body of work to be able to get to what it means to extract storyline from long form video? I would also say that I think that NLP and NLU is really kind of ahead of the curve, in my opinion, in this space. And the vision language models and the lot of action that we are seeing there gives me hope that we would be able to make use of all the great work that has been done in the NLP space for summarization to then bring it over specifically for the long form content understanding space. But I think that, it's a critical problem. Without getting there, I don't think we would have really achieved long form video understanding, because that's a defining unique aspect of this space. And I think a lot more work needs to be done. Definitely.
Yeah, I think it's time to redefine some critical research problems in this domain. Cool.
Yeah, so I think thanks again for Rafay giving such a great talk and answer our questions. So thank you.
Thanks for inviting me. Thank you.